Welcome to this explainer. I want you to take just a quick second to look around the room you're sitting in right now. The lights, your computer, maybe the phone you're holding, they are all powered by this invisible, totally silent flow of energy. We interact with this unseen force dozens, if not hundreds of times a day, usually without giving it a second thought. But beneath the surface of our walls and inside our devices, there is a beautifully structured, highly predictable ecosystem at work. Today, we're going to explore the fundamental principles that govern this system. We're going to demystify the rules that bring our technology to life, and we'll do it step by step in a way that makes complete sense. So it brings up a beautifully simple, relatable question, right? What exactly happens the exact moment you flip a switch? In a fraction of a second, a room goes from dark to brilliantly illuminated. But how? How does the stillness of a disconnected wire suddenly transform into a dynamic, roaring flow of energy that can heat an oven, spin a motor, or power the entire internet? That exact moment of transition is the core mystery we are going to unravel together today. Okay, so here is our low-pressure roadmap for today. First, we'll cover the foundations of electrical charge. Second, classifying network elements. Third, we'll learn the rules of the road with Kirchhoff's circuit laws. And finally, we'll wrap up with reactive circuits and time. We'll build this up layer by layer. All right, Section 1, Foundations of Electrical Charge. Let's start with the absolute physical reality of what makes electricity actually happen. Everything literally starts right here, with charge. Now, charge isn't some magical, invisible force. It is a fundamental physical property of a particle, exactly like mass. Protons carry a positive charge, electrons carry a negative one, and we measure this entire property in coulombs. These tiny charged particles, they are the absolute foundational building blocks for everything we're going to talk about today. And once you have charge, well, the next natural step is movement. That's current. It's basically the organized, continuous flow of these tiny charged particles. When you see the equation I equals dq over dt on screen, please don't let it stress you out. It's honestly just a mathematical way of measuring the traffic. It's just the change in charge over a specific amount of time. You're simply measuring the speed and volume of the flow in amperes. But here's the thing. Particles don't just move entirely on their own. They need a reason. They need a push. And that brings us to electrical potential, or voltage. You can think of voltage as the actual physical work required to get those charges moving from point A to point B. It's work divided by charge. Basically, it's the energy you have to invest to create that roaring flow of current we just talked about. Moving right along to Section 2, Classifying Network Elements. Now that we have our basic building blocks, let's look at the different players or characters that actually live within these circuits. So our first major division of labor here is between active and passive elements. Active elements, like the batteries you use every single day, are kind of the generous ones. They're actually supplying energy to the circuit. Passive elements, on the other hand, like resistors, inductors, and capacitors, they simply receive that energy. They either dissipate it as heat or temporarily hold on to it for later. We can also classify these elements by how dependably they behave. A linear element is great because it cleanly and consistently follows Ohm's law. If you double the voltage across a simple resistor, the current perfectly doubles in response. It's a nice, clean, straight line. But a nonlinear element, like a diode, that has a much more complex curving relationship. It definitely doesn't play by that simple straight line rule. Then we've got the concept of directionality. A bilateral element, like your standard resistor, honestly doesn't care which way the current flows. It behaves exactly the same whether the traffic is moving left or right. But a unilateral element, again, like a diode, acts like a strict one-way street. Its behavior completely depends on the direction the current is actually trying to go. And our final classification is all about physical space. A lumped element is probably what you picture when you think of electronics, a discrete, distinct little resistor or capacitor that you can physically pick up and hold between your fingers. Its properties are lumped right into one spot. Distributed elements, however, are totally spread out. Think of a massive, continuous, high-voltage power line stretching across the countryside. You can't just unclip the resistance from it. The electrical properties are distributed along its entire endless length. All right, Section 3, Kirchhoff's circuit laws. How do all these distinct elements actually behave once they're connected? Let's look at the dependable rules of the road. First up is Kirchhoff's current law, or KCL. Basically, at any junction point, which we call a node, whatever electricity enters absolutely must exactly balance out what leaves. It's honestly exactly like water gracefully flowing through branching pipes. No charge mysteriously vanishes into thin air, and no charge is magically created. It is a perfect continuous accounting system. Then we have KVL, Kirchhoff's voltage law, which applies to closed loops. If KCL is about traffic, KVL is all about energy. As you trace a complete path around a closed circuit, the total voltage supplied perfectly matches the voltage drops, meaning by the time you return to your starting point, the net change in potential is exactly zero. The system fundamentally just seeks to balance itself out. Finally, Section 4, Reactive Circuits and Time. Up until now, we've only really talked about steady states. But what happens at the exact moment of change? Now, I know these concepts involve differentials and integrals, but please don't let the calculus overwhelm you here. Let's completely de-escalate this for a second. The core concept is actually deeply intuitive. Inductors and capacitors are simply elements that fundamentally resist sudden, jarring changes. Think of them as nature's shock absorbers for electrical circuits. Let's watch how an inductor reacts. Right before we flip a switch, everything is still. That's our steady state. But at the exact moment of change, the very instant that switch closes, the inductor essentially says, hold on, not so fast. It acts as an open block, completely refusing to let the current change instantaneously, which protects the system. Then, as a little time passes, it relaxes, eventually letting current flow freely as if it were just a regular wire. Now, a capacitor does something pretty similar, but it protects voltage instead of current. When the switch is suddenly flipped, the capacitor won't allow the voltage to jump instantly. In that initial fraction of a second, it acts like a short circuit, just absorbing the sudden impact. Given enough time, the dust settles, it fills up with charge, and then it blocks further direct current flow. So both of these elements are really just working to ensure transitions are smooth and managed. So when we pull back and look at everything we've covered today, I really hope you find a sense of peaceful realization in all of this. Because no matter how complicated an electrical schematic might look, or how intimidating a piece of modern technology seems, it's all built on these same exact foundations. Complex circuits are really just elegant combinations of simple elements, your resistors, capacitors, and inductors, all faithfully obeying basic, reliable rules like KCL and KVL, and constantly, always, seeking equilibrium and balance. We've seen how this simple flow of charge completely dictates the behavior of the technologies we rely on every single day. By understanding just these few basic principles, the chaotic mess of wires hidden behind your walls suddenly becomes a rational, highly predictable orchestra of physics. And it kind of makes you wonder, doesn't it? If the intense, hidden energy of electricity is governed by such clear, calming rules, what other invisible, predictable rules might be governing the seemingly chaotic systems around you in your everyday life? Keep your eyes open and keep asking questions. Thanks so much for joining me for this explainer.